Hello and welcome to lecture number 2. Here we'll see what is an assertion and what are the benefits. So assertion is simply a check. Some people may also call it a checker. But assertion is simply a check against the spec of your design. And you want to make sure that you have an assertion that tells you if the spec is violated. So let's take a very simple example, which will be much easier to grasp the concepts with. Let's say a frame is deasserted, meaning it goes high, it's an active low signal, that the last data phase is asserted, meaning it goes low, within 2 clocks. So here's clock number 1, when the frame is detected to go high. Here's the first clock after which LDP is detected to go low, or it may go low after the second clock. In either case, if it goes low after the first clock or the second clock, that the assertion is supposed to pass. If not, if it doesn't assert within the 2 clocks, the assertion should fail. So I've repeated the diagram here again. Now let's see, the first question that may come to someone's mind is saying, hey, I've been using Verilog for such a long time. Why can't I just use Verilog? Okay, this is how we write the code for this particular check. There are many ways to write it. This is the preferred way that I would write it. Basically, you'll have to fork off 2 procedural blocks within a fork join. And when either of the block completes, you'll have to disable the entire begin end block. Now, without going into too much detail of how exactly this code works, I just want to highlight that this is slightly complicated code. There's a very good chance that if you don't put this condition correct, neg edge LDP, or repeat 2 pause edge clocks, and if you prematurely disable the LDP check, there's a good chance you may get a false failure. And you don't want that. So there is a good chance that you will end up spending more time debugging your checker or your Verilog assertion compared to the design itself. Now let's look at how the SystemVerilog assertion code would look like. And we'll go into plenty of details. So for now, just accept it the way it is. So what we do is, at pause edge of clock, these are the clocks, at pause edge of clock, if $rose frame, that means frame rises, goes from 0 to 1, that within the next 2 clocks, 1 or 2, that LDP should fall. As you can see, this is very intuitive, very readable, and very easy to develop. Then you assert the property and then you cover the property. And again, we'll see what all these things mean. But the point I want to make sure is, if I read this assertion, I know what I'm trying to check. If I read this Verilog code, honestly, it'll take me some time to figure out what is it that I'm even trying to do here. So assertions shorten time to develop. That is a major benefit of Verilog assertions. Now let's see, how does it help shorten the time to debug? Let's say this is your typical design. You have flop state elements, then you have logic here, within which you have FIFOs, state machines, and counters. Well, this design is not good, so there's a good chance you have bugs everywhere. You apply the stimulus, you look at the response, and what do you normally do? Okay, the test fails. So you start debugging, you keep going back, till you finally figure out that the FIFO overflow condition had violated. And finally, you'll fix it. But it takes you a long time to simply go through this. And that's what I mean by saying that basically what we normally do is we do a black box verification, which is fine, but the observability is also black box. You don't know where things went wrong. Now let's say you embed or you apply assertions around the FIFOs, around the state machine, and around the counter. What that means is, let's say you have this check or assertion which says if FIFO is full, you won't write anymore. If FIFO is empty, you won't read anymore. So you write all these different kinds of assertions around the state machines. For example, state machine check could be that state 3 must go to state 2 and not vice versa. For example, state 2 cannot go to state 3. So you have these assertions embedded, and now the test fails. When the test fails, one of these assertions is going to fire. And right away you'll know, oh, it was a FIFO overflow condition that failed. So you don't have to backtrace like you normally do. So what that I call is black box verification with white box observability. So bottom line is it improves observability and thereby it reduces time to debug. Now, how does it help you to determine if you have covered all the conditions that you were supposed to test? Even there, SystemVerilog assertions come into picture. So for example, we can cover FIFO state machines and counters just like the previous design. And we can cover inputs, intra-module, intra-block interfaces, and chip I/O interfaces. What it does is, at the temporal level, for example, we say that FIFO overflow or FIFO full means you should not write. So what we can do is cover that condition, meaning we will know that we did exercise the FIFO full condition and the assertion failed or did not fail. These temporal domain conditions, and we will see a lot more on that, are essential to make sure that your test bench have indeed exercised the condition where you made sure the FIFO was full. Without such cover, you will not know. For example, let's say an assertion fails or an assertion never fires. FIFO full meaning you should not write. That assertion never fires. So you may think, oh wow, my logic is good. Whenever there is a FIFO full, I never write. Not true. What if you never actually exercise the condition FIFO full? Assertion has no clue. Cover will tell you whether you even exercise that condition or not. So basically, an objective measure to knowing have we verified everything is done by the cover statement. There are many other advantages. For example, there's not a single design that at least I can think of which is singly clocked. So the multiply clocked assertions help you with that, specifically the CDC logic, clock domain crossing logic. The other thing with the assertions is that they can be parameterized. So for example, I'll create a library with different kind of assertions, but they are parameterized. I won't hard code them, just like a task or a function for that matter. You will write an assertion for a 16-bit bus interface and then parameterize it so that the formal and actual you can change it to 32-bit bus interface. And very important point I want to mention here is the cleaner separation of RTL and DB logic. If I'm in management, I would never want to see any code in the RTL design other than the code that is going to be synthesizable. So embedding assertions within RTL is very, you'll end up with a spaghetti code. So what this SVA language allows you to do is you keep your assertions outside of RTL and then you quote unquote bind your RTL design with your assertions. And the other important advantage here is that this so-called bind, and bind is a keyword by the way, it works for both Verilog and VHDL. So you can have your entire RTL in VHDL for that matter. You can write your assertions in Verilog and then you can bind the Verilog assertions, SystemVerilog assertions with VHDL. This is a very powerful feature of the language. Another thing you should note that assertions are always on. What that means is, let's say an assertion fires and then you actually fix it. You think you have fixed it, but the assertion is still active. Just because you fix it, the assertion doesn't care. It's still active. There's a good chance some other test number 100, may still fire it and you will realize your fix was not good. All the assertions are always active. That means the more tests you add, the more assertions may or may not fire until the end of the day, including you go from directed to constrained random to random, assertions will fire if there's a bug. And also note that in recent days, the assertion synthesis has taken off. What that means is you write the assertions, they can be synthesized, they can be converted into gates, and then you can use this assertion, which is quote unquote now part of the design. You can put that assertion into the acceleration box or the emulation box. And this is amazing because then whenever an assertion fires within the emulation box, for example, you can write to a debug register, and then you can, for example, boundary scan it out or ATPG scan out, and then you will know exactly where the design failed. Right now, when you do emulation or acceleration, it is pure black box. Emulation will run in 2 seconds, for example. It will take you 2 hours to debug if something fails. But with synthesizable assertions, it is much more easier and productive to work with emulation or acceleration boxes. More advantages, the language allows global severity levels, so you can have a uniform error reporting structure. You can globally turn on or off assertions. You don't have to have control over individual assertions. Just like you must be familiar with dump on, dump off. For example, during reset, turn off all the assertions. Once the reset is over, turn on all of them. Another advantage, and you may or may not be familiar with static formal verification, is that a formal verification is such that it will, for a given cone of logic, it will apply all possible combinations of the input in both combinatorial as well as temporal domain. This is different from writing your own test bench. It's exhaustive. And what the assertions language allows you to do is it tells you that, okay, out of the 20 inputs, assume that certain inputs will always be, for example, 1 or 0. This is very useful for a static formal verification tool, because one of the problems with static formal verification is that there is something called logic cone explosion problem. There are 20 inputs, each one can be in any condition, and in temporal domain they can each vary within the 10 to 20 clocks. There are so many combinations, and for a formal tool to verify all those combinations, it may give up or it may take forever. So the assertions language allows you, with a construct called assume, to reduce the scope of that cone of logic. And that way, your success of verifying a given, for example, FIFOs are prime candidates for formal verification. There are so many conditions exist around FIFO. You write a test bench and there's a good chance you may miss verifying a particular given condition. Formal verification allows you to do that. And the next advantage is obviously, like I just said, in this one language. You can assert, you can cover for functional coverage, and you can assume for either constrained random verification or for static formal verification. This one is to show what I just basically described. So you have the SystemVerilog assertions, and within the assertions you have assumptions, assume, the keyword we just saw. This assume and the assertions go into apply to your DUT, and during formal you can go through the formal verification, and there are new tools that also allow you to do static functional plus simulation. What that means is, again, back to those 20 inputs, there are so many combinations. So what the hybrid does is it simulates up to a certain point and knows the input values of some of the input values of those 20 inputs and says, okay, No need to exercise these 5 inputs or 10 inputs. So that's hybrid. And so basically assertions are applied on the formal side, and assertions are also applied on obviously the simulation side, which is the simulation side is what we are going to discuss in this course. And then between these two, you will exhaustively verify a given piece of logic, a given subblock, or the chip itself. And then you will know whether the property passed or failed. Some methodology guidelines on ABV. So things have changed recently where the agreement or disagreement on who should add the assertions is slowly thinning away. But I just want to make sure that the design engineers say, hey, writing assertions is a verification engineer's job. They are verifying the design. Verification guy says, oh, wait a minute. I don't have the knowledge of your microarchitecture. I don't have the knowledge of your interblock interfaces. So you need to write some assertions in that direction. So what's the answer? The answer is both of the design and verification engineers need to add the assertions. Let me give you some example. So design engineer will have to write microarchitectural level decisions and assumptions which are not visible to DB engineers. Okay. One of the rules that I can impart on you that you can take with yourself to your project meeting is that there are a lot of assumptions that design engineers make. If you assume that the request you send to the other block will always get an ACK into clocks, that's an assumption. So convert that assumption into an assertion. It will go a long way. You will know right away if that particular spec is violated. And keep doing so during your design process. And don't write all the RTL and then say, okay, now let me add the assertions. So what does the DV, design verification engineer, does? The design verification engineer, it basically stays at the macro level because the DV engineer doesn't really need to know, or should know for that matter, microarchitectural level detail. So for example, the DV engineer will say once the packet has been processed for L4 layer, that it will indeed show up in the DMA queue so that it can be transmitted out on the voice queue, for example. The DB engineer doesn't care exactly what kind of FIFOs the packets are being stored in and how the L4 layer processes it. This is the spec. That's what should be met. For example, a machine check exception indeed sets the PC to exception handler address programmed in the exception register. That's all you care. You don't care how the address is being, moved around to get to the PC. So this level of assertions are always added by the DV engineers. And DV engineers are also responsible for writing IO logic. After very simple assertion, and believe me, this will go a long way if you apply it. After reset is deasserted, meaning, hey, let's go, none of the signals should ever go to X. Write this simple assertion for your project after this course and you'll see the benefits right away. Or for example, if the processor is in wait mode and no instructions are pending, that it must assert a sleep request to memory subsystem within 10 clocks. Or another example, on critical interrupt, the external clock and control logic must assert CPU wake up within 10 clocks. We don't care. We meaning the design verification engineer doesn't care exactly how the logic is implemented, but this is what should happen. So that's what the DV engineer does, and that's what the above section shows what the design engineer does. Let's look at a case study. Let's look at the PCI. This is the parallel bus, which is a predecessor of PCI Express. And here's a simple protocol. You have the address and data bus. You have the command and byte enabled bus. You have the initiator ready. You have the target ready, and you have device select. And frame is what starts the whole bus. I don't want you to go through this whole protocol because that's really not important at this time. What is important is, given this particular protocol, what is it that the verification team will add? What kind of assertions they will write? So they will basically say, write assertions like this. For example, and this is the name of the assertion that I have come up with. You should always give a meaningful name to an assertion. On the falling edge of frame, AD and CBE cannot be unknown. Or when both iReady and tReady are asserted, AD and CBE, command and byte enable, cannot be unknown. Or when a frame can be deasserted, this is a good one, only if iReady is deasserted. And tReady can be asserted only if device select is asserted, and so on and so forth. So these are what I call macro level or high level assertions that the verification team needs to write. What does the design team do? So the design team, internal to the microarchitecture, they will say, for example, PCI state machine, if it's in the address CBE state, the first clock edge when frame is found asserted. Whenever frame is asserted, the PCI state machine must be in the address CBE state. That is their internal state machine assertion, which the DV engineer doesn't know. Or the PCI state machine is in data transfer state only when both iReady and tReady are asserted. Internal to their logic, they should not start transferring data unless and until both iReady and tReady are asserted, and so on and so forth. So do visit these slides again to see how or where a DV engineer comes into picture and where a design engineer comes into picture. So the next question is, okay, what type of assertions should we add? What is it? Just interface, or what is it? RTL assertions, meaning what is your design intent? This is where again intramodule design engineers come into picture. And what does RTL assertion mean? Illegal state transition. State cannot go from 2 to 3. It can only go from 3 to 2. Deadlocks. We know deadlocks. The state machine just locks dead. It just doesn't move. Live locks. Do you know what a live lock is? Live lock is when two state machines keep bouncing between two states. They still are, the simulation clock is still moving forward. It's like in a corridor, there are two people. One goes left, the other goes left to let the other one pass. Then the first guy goes right, the other one goes right. So they are both moving, but they are not able to cross the path. That's a live lock. And similarly, you have 5-4s, 1 hot, etc. Module interface assertions. Intermodule protocol verification. Illegal combination. ACK cannot be 1 if rec is 0. Steady state requirements. When slave asserts write queue full, master cannot assert write request. So RTL assertions, module interface assertions. The third one is chief functionality assertions. A PCI transaction that results in a target retry will indeed end up in the retry queue. This is a DV engineer's job where a macro level or a high level directly related to the spec, you write an assertion saying this must happen. And then of course the IO interface assertions. And here I just want to point out that there are a lot of commercially available standard bus assertions, VIPs. VIP stands for verification IP, that can be used comprehensively to check for design's adherence to the standard protocols such as PCI-X, PCIe, AXI, AHB, AMB, etc. And finally, this is the one type of assertions that many engineers miss: performance implication assertions. My background is pretty much from the processor design and the cache subsystem design. If I do not make sure during my design that the cache latency for read is, let's say, supposed to be 2 clocks, but I don't make sure till halfway through the design, I'm in big trouble, because you cannot fix this particular type of a problem without major architectural changes. If you write a simple assertion which says that, hey, latency, I must get my read data back within 2 clocks, then it will go a long way, because during the initial debug of the design, you will catch it. Similarly, for the network processor packet processing latency, if you don't have the correct latency for a VoIP kind of an SoC, when the voice packets come in and you convert them to voice, the voice will be broken because the latency is too high, not acceptable. So performance implication assertions is something many people miss, and I would like you to make a note of it. Okay, how should we add assertions? Most important rule is do not duplicate RTL. If A is equal to B plus C, do not write an assertion which says that A implies that B plus C equal to A. It has no meaning, because you are simply duplicating the RTL. If RTL has a mistake, well, your assertion has a mistake. So the important thing is to capture the intent. Intent can also be read as specification. For example, a write that follows a read to the same address in the request pipe will always be allowed to finish before read or after read, depending on your specs. That is the intent of the design. Again, and as I said before, and I cannot emphasize this more, add assertions throughout the design process. Do not wait and do not add them as an afterthought. If an assertion did not catch a failure, let's say you ran a test and the test failed and none of the assertions fired, and then finally you go this wonderful black box observability debug process, go back and back and back, and finally find where the bug is, you should note that if I had put an assertion there, I would not have to go through this trouble. So this is another way to know how to add assertions, that assertions sometimes you may miss. And if the test fails and does not get an assertion doesn't fire, then you need to add new assertions. And like I said before, create libraries of common generic properties, parameterize with formal arguments so that you can reuse them from project to project. There is also from Accelera organization, there is an open verification library, and you can actually use this directly. It's available, it's free. And the good news is this open verification library was initially written in Verilog with very long, cumbersome code that some really good engineers debugged and made sure works. But now they have taken the same quote-unquote checker or Verilog check and converted that into an SVA language. So please go to the Accelera.org, download the OVL library, and right there you will see a lot of examples of how you can write an SVA assertion. It'll be a great boon to your productivity. Okay, I think we have covered the benefits and how to add the assertions and so on and so forth. These are the guidelines that you will need during your project execution. Please use them. Please revisit this lecture. Thank you so much, and I'll see you in the next lecture. Thank you.